All right, so let's talk about counting techniques. So the first thing that you want to understand is the difference between the addition principle and the multiplication principle. So when it comes to the addition principle is all about combining events that are kind of separate, like they're disjoint, we would say. And then multiplication principle is all about looking at how many ways can things happen if I do them in a sequence, right? So the key word, honestly, is sequence here. So the addition principle is basically this. Let E1 and E2 be, we would say, disjoint events, meaning they have no overlap. There's no overlap between them. So nothing in common. So let E1 and E2 be disjoint events, nothing in common. And E1 has M outcomes, and E2 has N outcomes. Okay. Then the total number of outcomes for E1 or E2 is their sum, M plus N. That's it. And so basically, this will happen when you're trying to essentially look at different things at the same time. So, for example, when we were looking at the outfit example, I made the comment that when you're finding an outfit, you're going to use the multiplication rule to basically figure out, an outfit for a shirt. But the thing is, if you have more than one shirt, you can't wear the same shirt. Uh, you can't wear two shirts at the same time, essentially. So each shirt is separate from the other shirt. So at the end of all of it, we add them up together. So that's kind of the basic idea. But let's just do a very simple example. Okay. You have a choice of 5 beef dishes and 8 chicken dishes. How many options do you have? So I didn't ask you how many ways can you eat a chicken or beef dish. I just asked you how many options you have. And that's really what the addition principle is all about. It's just like, how many things do you have to choose from in total, right? Well, it's just 5 plus 8, which is 13. So that's like my total options. So when you're doing some of the multiplication rules, like, problems, you first actually have to use addition to set it up, right? Like, how many letters do I have? How many digits do I have? How many, options do I have? That's the addition principle. It's just taking all of your options and then start to multiply them or pick them or order them, right? That's kind of the whole idea. So now we're going to talk about the multiplication principle. So the follow-up to that is the multiplication principle. And this is the one that you're actually going to use the most, but I will show an example where you combine the two because sometimes you have to, right? So the idea here is let E1 and E2 be events with M and N possible outcomes, respectively. Then the total number of outcomes for a sequence of two events, E1 and E2, is m times n. Okay? You just multiply them together. So let's just do some examples. And again, sometimes there are so many like fancy ways that you can do this, but also you want to sometimes just think about it in the simplest way, right? So I'm just going to grab a random example from the internet just to illustrate this right here. So suppose there are 3 major auto routes from Washington, D.C. to Chicago and 5 from Chicago to Los Angeles, right? How many routes are there, right? So how many routes are there? Well, again, it just kind of depends on how you want to interpret this, but effectively, I just want to find out how many routes are there from DC to Chicago, and it's just we're going to multiply, right? So if you're going from Washington, D.C. to Chicago and then Chicago to L.A., so basically you can think about it this way. So again, there's several ways you can do this, but if you do D.C., then you have 1, 2, 3, and each of these routes will take you to Chicago, right? So Chicago, Chicago, and then Chicago, right? And then each of these will have 5 routes. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and they all take you to LA, right? So if you add all of the different routes, so route 1, route 2, route 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, you add up to 15 routes, right? So, or how many ways can you get from DC to Chicago? Well, there's 3 ways. And then how many ways can you get from Chicago to LA? Well, 5, right? So 3 times 5 is 15 routes, right? So that's effectively what I'm asking. How many ways can I get from one place to the next place? And then I have all of these different ways in between. So then you can make these a little bit more challenging because I can start adding restrictions to you, okay? So, for example, in this problem on the review, we say, okay, you're going to eat a meal consisting of an appetizer, a soup, a main course, and a dessert. There are 5 appetizers, 5 soups, 6 main courses, and 6 desserts. Your diet restricts you between choosing a dessert and an appetizer. You cannot have both. Given this restriction, how many 3-course meals can you have? Okay. So if we count, there is 1, 2, 3, 4 courses, but they ask for a 3-course meal, right? So using that, like I say, I like to, set up the little hangman. That's what I call it. I don't have any other way of calling it. So 1, 2, 3. So this is course 1, this is course 2, and this is course 3, right? Now here's the cool thing. It doesn't matter in this case if I eat dessert first or soup first or anything like that, but you'll kind of want to just follow in line of how they word it. That's typically just the most intuitive way, right? So first thing is I'm going to eat an appetizer. But the thing is, if I want to eat an appetizer, I can't have dessert. Okay, but if I want to eat a dessert, I can't have an appetizer, right? So then what you could actually do is this. You could say like, well, if I can only eat one of them, then they're essentially all the same thing to me. Like an appetizer and a dessert are the same. So you could put it in course 1 or course 3, but we could just say this is going to be your apps plus dessert. Okay, because they're effectively all the same because they're all unhealthy for you, right? So effectively course 3 is my unhealthy option. So if I take the number of appetizers and the number of desserts, which is 6, I have 11 options, right? And then for my soups, I have 5 options, so soup. And then for the main courses, I have 6. So 5 times 6 times 11. And if I multiply those all together, I should get 330. Yep. So 330 meals like that. And so that is the interpretation. So then this kind of idea leads into permutations. Okay, so we can start talking about permutations and the fundamental theorem of counting. And the fundamental theorem of counting, honestly, is just the multiplication rule. It's just, we can go further than that, right? So if you have n options and no repetition, okay? So you have n options and no repetition. Actually, there's one other condition too. So n options, no repetition, and all items are unique. So there's a difference between repetition and being unique slightly, because it's just a way of describing it. So all are unique. Then the number of ways of ordering n objects is n factorial, right? Which is just equal to n times n minus 1 times n minus 2 dot 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 3 times 2 times 1. So this is assuming that you're ordering everything. Okay, so that's why we call it the fundamental theorem of counting. You can just order everything. And then permutations is like, well, what if I don't want to order everything? Like I want to order some things, and that's the permutation. And then permutations can be expanded to just cover everything too. So a quick example, how many ways can you order 5 books? Okay, how many ways can you order 5 books? Well, if you are ordering all of them, then it would just be 5 factorial, which is 5 times 4 times 3 times 2 times 1, right? And that would be equal to, I believe it's 120, but I will double check. 120, yeah. But you could also just think about this in terms of the hangman game, right? So this is why I like doing this, because for most problems, it works out pretty well. How many books am I ordering? So you can do, or I have 1, 2, 3, 4, 5 books, right? I have 5 books. And then I ask myself, how many options do I have for the first book? So I have 5, right? First book. And then once you use a book, that book can't be in another spot because it doesn't exist in 2 different locations. There's no repetition, and that book is a unique book. There's no other duplicates or anything like that. So then I have 4 options for my second book, and then I have 3 options for my third book, and then I have 4 options for my, sorry, 2 options. I looked at the wrong number. And then I have 1 option, right? So as you're going down the line, you're starting to lose more and more options like that, okay? And then if you multiply all of these together, you get 120. And so the nice thing about this strategy is it basically takes care of permutations, because if you think about it in terms of permutations, you're going to have to remember that there's a formula to it. And I always tell students that formula, you don't really ever have to use it because you can kind of reason it out just by doing this, right? But we'll remind you of the formula just in case you want to use it. So with permutations, if you have n objects and want to order r objects, then assuming no repetitions and unique items, the number of ways of organizing our objects from n total objects is, so the notation that you're going to see the most is NPR or NPK. So it's going to be n factorial over n minus r factorial, like that. Okay. And then it is also multiplied by r factorial, like that. Nope, no r factorial. That's combinations. One step ahead of myself. So n minus r factorial. There we go. So that's your permutation formula. And if you're wondering, like, what does that denominator actually mean? Well, the thing is, it actually basically gets rid of the part of the factorial you don't need. Okay. So when you do the factorial, you have to do all of them. So if I want to order 5 books, then I have to use all 5 books, right? But what if I only want to order some of the books, right? So I don't need the third option, the second option, or the first option. So that's what the n minus r factorial does, right? So essentially, here's an example. How many ways can you order 4 books from 10? Okay. So again, if you just play the game that I've shown you, well, how many books do you have? 10. How many books do I actually want to order? I want to order 4 of them. So 1, 2, 3, 4. I only need 4. So then how many options do I have for my first book? I have 10 options. I've used a book. How many options do I have left now? 9. Okay, I've used the book. How many options do I have left now? 8. How many options do I have left? 7. Okay. So you can't do 10 factorial because 10 factorial would go all the way to 1. So effectively, okay, so the answer to this question is just 10 times 9 times 8 times 7. So 10 times 9 times 8 times 7. And we get 5040, 5040. So the formula says, okay, if I use the formula, it would be, so using the formula, 10 factorial over 10 minus 4 factorial, like that. So if I write out 10 factorial, that's actually not a very good way of writing it. Let me do this, dots. They look like a bunch of polynomials. Right? And then this is 6 factorial, so 6 times 5 times 4 times 3 times 2 times 1. Well, these all just cancel each other out. And what are you left with? 10 times 9 times 8 times 7, which is what we have right above, right? So that's what the formula is doing. It's just cutting out what you don't need. I don't need all 10 books to be organized. I just need the first 4. So how many options do I have for the first 4? I have 10, then 9, then 8, then 7. So I always tell students, you don't ever act, so like if you ever actually use this formula, like you use that formula specifically, you're kind of doing it incorrectly. You should never have to use that formula, like the factorial formula, because you can usually reason it out yourself or use a calculator. So never ever actually calculate the factorial yourself. Just use the NPR calculator. And so if you don't know how to do that, it's very simple on your calculator. I'll show you very quickly. So let me grab my calculator. So let me go to So here's my calculator. You're going to do second quit. So if you have a newer calculator, you should do this no matter what anyways. So the first number, n, is your total. And then this is what you have picked, right? So it's your objects, whatever you pick. So for me, it's going to be 10. So you have to type in the number first, your total, hit the math button, and then go to PRB for probability, and it's the second option right there. And then NPR, and then 4, right? And then 50/40, right? Or 10 times 9 times 8 times 7, 50/40, right? Same thing. If you have a newer calculator, yours might show up as like the actual P. But if you go into PRB and you just type in NPR immediately, you're going to get this A and S because it's just taking the last number that you had in the calculator as your placeholder. So that's why I tell students you need to type in the number first before you use this command. Otherwise, it's not going to like it. Okay, so that's how you do NPR. All right, so that's permutations. Kind of went out of order, I realized. So this is the permutations of all objects. Okay, so I'm actually going to write that here. So this is the ordering of all objects. And then I'm going to put in parentheses, no repetition. So it is a permutation, but a permutation of everything, right? And then this is permutation. So some objects, no repetition. And then the one that I skipped over, which I'll just do now, is the ordering of repetition. Okay. So what happens when you do have repetition? And this is like the actual like fundamental principle of ordering. It's just like there is no restriction. So basically, here is no restrictions. So let's do an example from the review. We'll do the first one. A 6-digit password is formed from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many different passwords are possible if digits are repeated? Okay. So again, we want 6 digits. So 1, 2, 3, 4, 5, 6, right? That's it. And then how many digits do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits. Yep. And so then you ask yourself, how many options for the first digit? So I have 10. And then how many options for the second one? Well, they said repeated, so 10 and 10 and 10 and 10 and 10. So you just multiply it. So times, 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 times. And it's just going to be 10 to the 6th power, right? Or you could write that out and that'll be your answer. So I think that's 1 million. Now, the next question adds restrictions. So repeated one is like the most general. There are no restrictions. And that we call the fundamental theorem of counting or the principle of counting because there are no restrictions. You just multiply all your options. And then permutations is, okay, now we have a restriction, no repetitions. And then combinations like, okay, we don't even care about order anymore. So let's get rid of that too, right? So as you're going and adding more restrictions, things get smaller, right? Things get smaller. Okay, so I still have 6-digit password, 1, 2, 3, 4, 5, 6. But now for the first one, I have 10. I still have 10. But once you use one number, you can't use it again, right? So then you have to go down to your second one. Now you have 9, and then 8, and then 7, and then 6, and then 5, right? And so if you multiply that out, you get 151,200. If you really think about this, this is just 10, and we're permuting 6. 10p6, right? So if I go to my calculator, 10 math, PRB, NPR, 6, and we get the same number. So when you don't have to order everything, you can just use a permutation, right? Now, then the question becomes, how do I know it's a permutation versus a combination? Order. That's the key thing, is order, right? So let's do another problem from the review. A professor wants to award prizes for first, second, third, fourth, and fifth place in a class of 30, right? And how many ways can the prizes be awarded, assuming no ties? So if someone gets first place, that is different than getting second place, right? So there is a sense of order, some natural sense of order, right? So again, step 1 is just make your hangman. So I got 5 prizes. 1, 2, 3, 4, 5, because I have 5 prizes. So then, how many students can get first place? Okay, so I have 30 students. So 30 people can get first place. But once a person gets first place, they can't get second place too. So then, my second place. And then my third place. And then my fourth place. And then my fifth place, right? And then you just multiply all of these. And so if you do 30 times 29 times 28 times 27 times 26, you're going to get really big numbers, 17,100,720. But again, you have 30 students and you are ordering or permuting 5 of them, right? That's what you're doing. 30 students, ordering 5 of them. So 30, math, permute, 5, and I get the same number, right? So that's permutations. Any questions so far? All right, so looking at some of the passcode problems, like a password can have 6 or 7 digits. Digits can be repeated and zeros are allowed in the front. So 1, 2, 3, 4 is a 4-digit code and 0, 1, 2, 3, 4 is a 5-digit code. Sorry. And those wouldn't work. That means no 6-digit code will ever work for a 7-digit, and no 7-digit code will ever work for a 6-digit. So they are completely separate. So that's where that addition principle is going to come into play. You have to do one for the 6 digits and one for the 7 digits, right? So step 1 is to set up your hangman. So for the 6 digits, 1, 2, 3, 4, 5, 6. And then for the 7 digits, 1, 2, 3, 4, 5, 6, 7. So these are the 6-digit, and these are the 7-digit. Okay. They can be repeated and leading zeros are allowed, which means you have to remember this. There are 10 digits, 0 through 9. That's just something that you have to remember. And so for the 6-digit, I have 10, 10, 10, 10, 10. If it wasn't repeated, then I would have to go 10, 9, 8, 7, 6, and then 10, 10, 10, 10, 10, 10. And then I multiply all of these together. And that's just going to be 10 to the 6th plus 10 to the 7th power. And that will be 1 million. Is that a million? 1, 2, 3, 11 million. Yeah. 11 million. So this is where you have to use the addition principle because, again, they don't share codes. And so what if they give us some like very restrictive parameters, right? And from a security perspective, more restrictions actually makes your passwords less secure because ultimately that limits the number of options that you can have. I guess the only argument against that is sometimes the reason they do that is because they want to eliminate super common, easy passwords that people just default to. So like 0000, like all zeros, they don't want people to use that code. So they remove like where you can repeat zeros or something like that. Just because of that, because people's natural habit is to pick the easiest password. So yes, they reduce how many passwords there are, but what they're really trying to do is reduce all the easy passwords so people don't pick those. Okay. So it says that's exactly 7 digits. 1, 2, 3, 4, 5, 6, 7. Okay, digits cannot be repeated. And it must begin with an odd number. So that's 1, 3, 5, 7, 9. And then zeros cannot be used anywhere. So they say no zeros. So that means I am left with 1, 2, 3, 4, 5, 6. Forgot the 6. 7, 8, and 9. So I only have 9 options total. Okay. So it says the passcode must begin with an odd number. So this one right here has to be odd. So how many options do I have? I have 5. So then I do 5. But, okay, now it used to be 10 because I had 10 digits, but they said no zero. So now I have 9, right? Except you have to remember, it would have been 9, but we used an odd number already. So this one has already been used and you cannot repeat. So you actually are down to 8. Okay. You can't use 0 and you can't use the first number. So let's write that down. No 0 and not the first number. So that one actually starts at 8 instead. And then now I just go down by 1 because now I just can't use the previous one. So is this a permutation problem? You can make it a permutation problem, but I'm telling you right now, it's a lot more complicated to think about it like that for most students. Okay, not everyone. Some people kind of get it, but in this case, it would be 100,800. So the way you could do it using permutations is you could say, I have 5 odd numbers and I got to pick one of them. Okay, so 5 permute 1, and then from there, I have 8 numbers left, and then I got to pick 1, 2, 3, 4, 5, 6. So I got to pick 6 of them. Okay. And now that I'm thinking about that, 5 permute 1. Does that make sense? Yeah, that should be fine. So let's just make sure that's correct. So if you want to do multiple permutations, you got to do parentheses, 5, math, PRB, permute 1. Close parentheses. Again, parentheses are important for these permutations. And then, whoops, I forgot the number. Don't forget the number. If you forget, do second delete for insert. 8, permute 6, and let's see if that's correct. There we go, same answer, right? Again, you don't have to do that. That's why I tell students the hangman's better, because you don't have to think about the permutations in that fancy way of like, well, how many options do I have for this one, and then I got to multiply them and then add them. If you do the hangman game, it does all that for you. And you don't got to think about it too much. Okay. Any questions so far? Okay. So how many different sequences can be formed using all the letters that are given? So you see the word sequences, the definition of permutation and multiplication, sequences, that matters. That means order, right? So how many words do I have? Letters. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, right? And so how many options do I have for my first letter? Well, I have 6. And then I can't use it again. 4, 3, 2, 1. So that's just 6 factorial. And if you do 6 factorial, 720, right? Just like that. Now, I didn't say it has to make up a word in English. It just has to be a sequence of letter. Okay, that's all. The next one, on the other hand, does cause an issue because there's repeated letters. And so part of the rule for permutations is no repetitions, okay? But what happens when you do have repetitions? Do you just give up and not do the problem? No, we actually have a technique for that. So for repetition, you divide out the repetitions, sorry, the repeated letters. So here's the formula. It's not a too terrible formula to memorize. So n is equal to the total letters. And then A is equal to number of repeated first letter. And then B is equal to number of repeated second letter. And so the formula is n factorial over a factorial, b factorial, dot, dot, dot. So you just keep dividing out the ones that repeat, okay? You can do the hangman game with this. It's the same principle. So how many letters do I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 letters. So n is equal to 8. And then do I have any repetitions, right? Well, just E. So E repeats, and that's the only letter that repeats. So E repeats twice. So A is equal to 2. And so if you just plug into that formula, you get 8 factorial over 2 factorial, which would be equal to 20,160. Okay, just like that. Or if you do the hangman game, you do 1, 2, 3, 4, 5, 6, 7, 8. So then you just do it letter by letter, right? So how many options do you have for the first letter? Well, I have 8, and then 7, and then 6, and then 5, 4, 3, 2, 1. But the problem is the two E's, you can't tell the difference between them. So if you swap the E's, the sequence looks the same. So I need to get rid of that. So I'm going to divide it by my first repetition. So how many E's are there? There's 2 and then 1. So I can basically divide out the first E and then the second E. And then that gives you 20,160. Unfortunately, when you get more complicated problems, the hangman becomes a little bit more difficult to use because then you have to start doing stuff like that. And so it does have its limitation. And then in combinations, hangman becomes very difficult because you have to divide out a bunch of things. And so that's where we actually do use the formula, but the calculator takes care of the formula for us. Now, theoretically, you could do it another way, but this would require you to think a lot more about it. So let's just pretend that we pick all of the letters and then the very last letter is E. Well, how many ways can we pick just E, right? So like I said, or you could do 1, 2, 3, 4, 5, 6, 7, because there's 2 E's, right? So you don't need, I mean, you do need, sorry, 8, because we got to make an 8-letter sequence. So assuming that we don't pick E first, we have 8 options, 7, 6, 5, 4, 3. And then when we get to the last one, the last 2 are E, right? So how many ways can I pick E? Well, there's only one way because it's just E. And then there's just only one way because it's still just E. So you could do it that way. It ends up working out. It's just that one requires a little bit of like, you got to convince yourself. And I don't recommend that one, honestly. So, but if you care to think about it that way, you can. All right, and then the last one from this same problem. So now excellence. So again, first just count how many letters you have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a total of 10 letters. And then which letters repeat? So E repeats, and it's going to be 3 times. 1, 2, 3, 4 times. And then X is 1, C is twice. And then L is twice. N is once, and I think it's all of them, right? So then the formula is n factorial over a factorial, b factorial, dot, 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 just however many times it repeats. And then we just plug in. So there's 10 letters. And then we got to divide out the 4 E's that repeat, the 2 C's that repeat, and the 2 L's that repeat. And if you plug that into your calculator, you get 37,800. Now, if you're wondering, how do I plug in factorials in my calculator? Well, I can show you that too. So 10 factorial, so 10, math, and then go to the PRB, and it's option number 4, the little exclamation point, divided by, left parentheses, 2 factorial is 2. You can do like the smaller ones I would recommend doing in your head, just so that you don't have to write out the factorial, because you have to go out of your way to find it. So 2, and then times 2 times 2, and then we get 37,800. Right. There it is. So nice little formula to kind of remember in case you have repeated. Typically, they don't usually ask these kind of questions on the exam because they're a little bit more challenging, but in case they do, there it is. Right. So that looks like it covers pretty much all the permutation type problems. Now we're going to want to look into combinations. So, and then that's pretty much the last thing. So combinations means, so when you're talking about combinations, we mean no order. So order does not matter. Some people like to do permutations is a, what is it called? No, so combinations is a committee. Permutations is, there was a P word that goes with it. I'll have to think about it. Like that. And then combinations, no order. So given n objects, if you want to select R objects, with no order, no repetition, and unique items, then the total combination of R objects from n total objects is, so we use NCR equal to n factorial over R factorial n minus R factorial. It's very similar to the permutation formula. It just has that extra R factorial. Okay. And then on the calculator, it's just math, PRB, option number 3. Okay. That's all it is. This one actually has several notations. The other most common one is this notation. We call that the binomial notation. That one's very, very popular. We're not really going to use it in this class, but I'm just telling you, if you look it up online, you'll see that. Okay. And let's just do some examples of these. Again, the whole goal here is like, we don't care about order. Like if I'm picking a group of 4 people, I don't care what order I pick them in. When you play poker, it doesn't actually matter how you hold the cards, right? The cards don't matter in the order in your hand. It's just what 4 cards or 5 cards you have. So let's just do a very generic problem. If you must select 6 out of 50 numbers to win the lottery, how many ways are there to do this, right? It doesn't matter if I pick 2 first or 3 first. It's the same problem. So, step 1, find total. So n is equal to 50. Step 2, find, how many you are picking. Well, I'm just picking 6 of them. And then step 3 is to plug in. 50C6, like that, 50C6 is equal to, so go to our calculator, type in 50, math, right there, and then 6, and then it's that really large number, right? 15,890,700. Not too bad. That's all combination is we don't care about the order. We just want to know how many ways can I pick something, right? And so let's look at the homework very quickly. And finish from there. So let's do the marble problem from 7.3. So a bag contains 2 red marbles, 5 green, 1 lavender, 5 yellow, 5 orange. How many sets of 4 marbles include one of each color other than the lavender, right? So if I have two red marbles, I really can't tell the difference between the two red marbles. So when I pick one versus the other one, like there's no ordering to them. So that's the other huge thing is when you have like indistinguishable things, that becomes more of a combination problem because you really can't order indistinguishable things, right? So effectively here, how many marbles do you want? You want 4 marbles, right? So there is an element of the hangman game in this, but I'm not going to just use a single number. So I have 4 marbles. 1, 2, 3, 4. Okay. And they say one of each color, but not lavender. Okay. So let's do the red marbles. I want 4, and I got red, green, yellow, and orange. That's 4 of them, right? So for my red marbles, I have 2, and I want to choose one of them, right? So 2, choose 1. And then for green, I have 5 of them, and I want to choose one of them. And then for yellow, I have 5 of them, and I want to choose one of them. And then for orange, I have 5 of them, and I want to choose one of them. And if you're wondering, why are you only choosing 1? Well, I need only 4 marbles. So 1 marble, 2 marble, 3 marble, 4 marbles, right? And if I multiply all of those together, 5 times 5 is 25, times 5 is 125, times 2 is 250. Now, here's the cool thing. If you ever have NC1, so basically NC1, it's just going to be equal to N. So if there's a 1, it's just N. And then if it's NCN, that is equal to 1. That's double equal right there. You don't have to memorize those. Your calculator can do it too. But sometimes if there's only 1, you can kind of do the math very quickly, right? And we did all the ones from the review. So all the review problems are done. And then I'm just looking through the homework to see if there's any other last little problems that I think we should talk about here. Okay, following up on this problem, so follow up. How many combinations or how many ways or how many 4 sets are there where 2 marbles are red? Okay, so 2 marbles are red. So again, how many marbles do you need? Well, I need 1, 2, 3, 4, right? I need 4 marbles. However, there is a restriction, and that restriction is the first 2, or the last 2, or the middle 2, it doesn't matter, but there's no ordering here. We need to make these red, okay? So 2 of the marbles are already, they're already picked for you. So that means this whole thing is actually going to become 1 line, and that's going to be 2, choose 2, because I need 2 reds, right? So 2 red marbles. And then for the other colors, I have no restriction, okay? The lavender restriction is gone. So then how many marbles do I have left? Well, I have 5 green plus 1 lavender plus 5 yellow plus 5 orange. And that's going to be equal to 5, 6, 16 marbles. Okay, that are not red. And so I have 16, and I got to choose one of them. And then once I pick 1 marble, then I got to pick another one. So then 15 choose 1, like that. Okay. And there it is. And so that's going to be equal to 15 times 16, which is 300. That doesn't sound right. Let me double check. That's not right at all. 15 times 16. 240. 240. Just like that. So 2 of the marbles have to be red, so I have to choose 2 of them from 2. And so that's just 1. There's only one way you can do that. And then I have 16 left, so not red. And then after that, I have to get another marble, so like that. And this isn't the only way you could do it. In fact, a lot of these problems, some people may see it one way versus some people may see it another way. So that's always something to think about is you're not always restricted to just one method, right? But any questions? All right, so that wraps up our review of chapter 7. Other than that, we're going to talk about chapter 8 the next day and go from there.